Hello everyone. Today we are going to explore a critical concept that ties together two major areas of computer science. First is operating systems and networking. So, the focus of our discussion is network organization concepts in operating systems. So, in the traditional sense, like an operating system is responsible for managing a computer's hardware and software resources. However, in a networked environment, the OS must also manage how computers interact and share resources across a network. This requires an additional layer of complexity and intelligence, which we refer to as network organization. So, let's just begin here. So, basically, um, if we talk about like what is network organization, like it refers to the architecture and strategy used to interconnect multiple computers, systems, and devices. And we'll also learn those architecture and those areas that we use now. Let's start by understanding the structure of networks. Now, starting with one of the most common types, the local area network or LAN. So, a LAN is a type of network designed to cover a small geographical area. This could be your home, a school, an office, or even a single building. So, within a LAN, multiple computers such as workstations, laptops, or mobile devices are connected. These computers often interact with peripheral devices like printers or storage arrays, and they are all usually connected to routers, which may also provide access to the internet or other external networks. Now, how are LANs constructed? Um, so LANs are most commonly built using Ethernet or Wi-Fi. Now, Ethernet is a wired connection defined by the IEEE 802.3 standard. Its speeds its speeds have evolved significantly, starting from 10 Mbps and now exceeding 10 Gbps, which is extremely fast and stable for many business environments. Wi-Fi, on the other hand, is a wireless alternative defined by the IEEE 802.11 standard. It typically offers speeds ranging from 11 Mbps to over 400 Mbps, depending on the version of Wi-Fi being used. Now, both of these standards, like Ethernet and Wi Fi, are constantly evolving, with newer versions providing higher speed, better stability, and enhanced security. Okay, now here now that we have defined what a local area network or LAN is, let's take a look at a visual representation to better understand how all the components come together. As shown in this diagram, a LAN typically includes multiple devices like laptops, mobile phones, tablets. All these can be part of the LAN. Now, these devices connect to a wireless access point, which provides them with wireless connectivity. Now, this access point is usually part of or connected to a router. You'll also see wired devices like a desktop computer or printer connected directly to the network, often via Ethernet cables. So the router serves as the central hub that directs traffic within the LAN and often provides access to a WAN link, typically the internet or a wider network like a corporate backbone. So essentially, this network structure shows how devices within a local space communicate with each other, share resources like printers or files, and access the broader internet through the WAN. So note the split in the diagram between LAN and WAN. The LAN portion handles internal communication while the WAN link is the bridge to external networks. This is a typical setup in many homes and small offices. As we move forward, we'll also look at other types of networks. Now that we have covered local area networks, so let's expand our view and talk about wide area networks or WANs. So a WAN links computers and networks over large geographical areas, often spanning cities, countries, or even continents. Unlike a LAN, which is localized, a WAN can connect multiple LANs together, allowing for communication and data exchange over long distances. So, WANs operate through point to point connections using a variety of technologies, including telephone lines, dedicated data lines, optical fiber cables, or microwave links, radio waves, or satellite communication channels. Now, these connections are typically managed by routers, which direct traffic from one network to another and ensure that data reaches the right destination. Now, what is the role of the internet? Now, when we talk about WANs, we are essentially describing the internet, also known as the World Wide Web. This global WAN enables devices all over the world to communicate with each other. Now, from your smartphone to servers across the ocean. So, WAN speeds can vary widely. So, we have first of all we have backbone providers which form the core of the internet infrastructure. They may offer speeds between 40 to 100 Gbps. In contrast, local internet service providers or ISPs usually offer much slower speeds depending on local infrastructure and demand. Now, the good news is that WAN links are constantly being upgraded, driven by the growing need for high speed communication. Now, if we talk about WAN and LAN interconnection, you can think of WAN and LAN interconnection like a cellular network. That means, like, your cell phone connects to a nearby cell tower using radio waves, and that tower is then connected to other towers or central hubs, forming a large scale network that ensures your call or data reaches the right place. Now, this same concept applies to computers. A device connects to a local LAN, which then connects to a broader WAN through routers or service providers. Okay, now let's take a closer look at the architecture of a WAN network, wide area network. Now, at the top of the image, you'll see a network host. This is any device that participates in the network. It could be a server, a user's PC, or a smart device. So inside the host, we have user processes. These are applications and services initiated by users, such as web browsers, email clients, or data processing tools. These processes interact with the host operating system, which manages communication with the network. Now, moving to the lower part of the diagram, we enter the communication subsystem, and this represents the actual WAN infrastructure. So, you will see multiple routers labeled R. These routers are responsible for receiving, directing, and forwarding data packets from one point to another across the network. Now the path a packet takes is determined dynamically based on availability, traffic, and cost. Now um, um, inters, interspersed among the routers are additional network hosts um, labeled H, and these hosts are connected to the network just like the one at the top, and they can send and receive data to and from each other across this router backbone. So essentially the diagram illustrates how user processes one on one host initiate communication, and the host operating system handles transmission through the network interface. Router manage traffic across the WAN, and ultimately the destination host receives the data. Okay. As we continue our journey into network concepts, our one critical topic to cover is naming and name resolution. Now, imagine for a moment you're trying to send a letter to a friend. You need their name and address, right? Now, the same concept applies in computer networks. So, every computer system within a network must have a unique name so it can be identified. Additionally, each process running on the set system, such as a browser, email client, or server, also needs a unique identifier, often called a process ID. But what happens when systems need to talk to each other across a network, like the internet? Now, that's where name resolution comes in. To communicate with a remote system, we need to identify it accurately. This is typically done using a host name, a readable name like www.google.com, instead of an IP address which is harder to remember. So we have a host name. So the process of converting a host name into an IP address is handled by a system called DNS, or the domain name system. This DNS is the internet's phone book. It translates friendly domain names into numerical IP addresses that computers use to locate each other. Now you will notice a reference to domain name structure. This is the hierarchy used in DNS naming. So, um, for example, in www.willy.com, this com is the top level domain. Willy is the second level domain, and www is a subdomain. Now, this structure helps in organizing and resolving host names efficiently. So, this is an example of DNS lookup. This code is in Java. Now, at the bottom of this slide, this illustrates how a DNS lookup works. Now, in this code, a hostname is passed as an argument. This program tries to get the corresponding IP address using inet address.getByName. Then If successful, it prints the IP address. If not, it catches an exception and prints an error saying the hostname is unknown. This is a simple but powerful example of how operating systems and applications interact with the DNS system to resolve names into address. Okay, now let's talk about a foundational concept in networking: communication protocols. Now, when two or more devices communicate across a network, they need to follow certain rules and procedures to ensure that data is exchanged correctly and efficiently. These rules are called communication protocols, and they are structured in layers. Now, let's look at the first three layers um, in this slide. Um, so, here we have um, physical layer, which is the first layer. This is the lowest layer and it deals with the mechanical and electrical aspects of data transmission. It's responsible for transmitting raw bits like 0 or 1 over a physical medium like a cable or through radio waves. Think of it as the wires, signals, voltages, and physical connectors. Second is data link layer. Now, the data link layer takes those raw bits from the physical layer and organizes them into frames, which are structured packets of data. It handles error detection and error correction. This layer ensures that the bits transferred are received correctly by the next device in the network. So, third, we have network layer. Here's where things get more intelligent. So, the network layer is responsible for routing. It determines how data packets travel from the source to the destination across complex networks. It deals with IP addresses, handles incoming and outgoing packet addresses, and manages routing information to respond to changes in network traffic. Okay, next, fourth, we have transport layer. Now, this is all about reliable delivery. It manages the transfer of messages between client devices. It splits messages into packets, ensures they arrive in the correct order, and controls the flow to prevent congestion. Um, it also handles error checking and retransmission if needed. Think of it as a delivery manager that makes sure that your package arrives safely and in the right sequence. Fifth, we have session layer. Now, the session layer is responsible for managing sessions between devices. It is simply a logical connection between two devices that are communicating. This layer starts, maintains, and ends these sessions, ensuring a stable channel for data exchange between applications or processes. Next, we have presentation layer. This layer acts as the translator. It takes data from the network and converts it into a readable format for the application layer. It handles tasks like data compression, encryption, decryption, and character encoding conversions. For example, when you receive a media file online, this layer ensures the formatting is correct for your system to display it properly. Last, we have application layer. So the this one closest to the end user. So it directly interfaces with software applications like your web browser or email client. This layer handles tasks such as file transfers, remote logging protocols, email communication, and database queries. Basically, it's where users interact with the network without needing to know the complexities underneath. Okay, now that we have explored the seven layers of OSI model in detail, and this diagram will help you to visualize how two computers communicate over a network using this layered structure. Now we have computer A and computer B. Each computer has its own set of OSI layers, from the application layer at the top down to the physical layer at the bottom. So, when a user on computer A sends a message or initiates a network request, the data travels down through all seven layers. Each layer adds its own headers and metadata, which helps in routing, delivery, formatting, and communication control. The physical layer then converts the message into electrical or optical signals and transmits it through the data network. This could be a cable, fiber optic line, or wireless connection. Now, next, the network transmission. Um, the data network, it's represented in the center, is where the actual transmission happens. This network is built on infrastructure that supports the lower three layers: physical, data link, and network layers. These three layers are typically implemented in hardware or firmware, like network interface cards, routers, or switches. Third, we have receiving side, like computer B. So once the signal reaches computer B, it travels upward through its OSI stack. Each layer decodes or stripe away the corresponding headers added by the computer A's layer. Now finally, the original message or data arrives at the application layer, where it is represented or presented to the user or to the receiving application. So this diagram builds on what we have learned so far, but now you can see the specific services and responsibilities handled by each of the seven layers of the OSI model here. Okay, now this diagram gives us a visual representation of how data is structured and transmitted across a network using the OSI model. This concept is known as data encapsulation. So, the vertical structure here represents how a message is built as it moves through each OSI layer on the sender side. Each layer adds its own header, and in some cases a trailer, to ensure the data can be correctly handled, routed, or interpreted at the destination. So the message starts in the application layer, as we discussed earlier. So this is just another breakdown with the key concept: encapsulation. So this layered addition of headers and trailers is called encapsulation, and it allows the network to handle complex tasks like addressing, routing, error detection, and session management in a modular and scalable way. So basically, the OSI model, which is Open Systems Interconnection model, was designed in the late 90s 70s to standardize how communication happens across diverse computer systems. It was built as a theoretical framework organizing communication into seven distinct layers that we have already discussed. Now, in contrast, the TCP/IP protocol stack is the one that actually powers the internet today. It's simpler and more streamlined than the OSI model. Instead of seven layers, TCP/IP uses four or five layers depending on how it's interpreted. And these layers combine the responsibilities of multiple OSI layers, making it more efficient, although sometimes more complex to implement because of that overlap. Okay, now on this diagram, we are directly comparing the OSI model and the TCP/IP model, which helps us understand how the conceptual framework of OSI maps onto the real world protocols used on the internet today. Now, on the OSI model, on the application layer, um, at the top of the OSI model is the application layer, and which provides services directly to the user. But in the TCP/IP model, this layer encompasses multiple protocols such as HTTP, DNS, Telnet, SMTP, and FTP. These are the things. In TCP/IP, there is no distinct presentation or session layer. Their responsibilities are handled either by the application protocols themselves or by the transport layer underneath. Then on the transport layer, so this in both models, the transport layer is responsible for reliable communication and end-to-end delivery. In TCP/IP, it uses two primary protocols here. First is TCP, Transmission Control Protocol, which is connection oriented, and second is UDP, which means User Datagram Protocol, which is connectionless and faster but less reliable. Okay, now next we have network layer. This is where routing and addressing take place. Like TCP/IP uses the IP protocol, Internet Protocol, to identify devices and route packets from source to destination. Okay, now next we have data link and physical layers. So in the OSI model, the data link and physical layers are separate and well defined. TCP/IP, however, does not define these layers explicitly. Instead, it assumes they are handled by the underlying hardware and network interface technologies, such as Ethernet, Wi Fi, or fiber optics. Okay, now that we have discussed how TCP/IP differs from the OSI model, let's walk through a real world example of how data actually travels across a network using the TCP/IP protocol stack. First, step one, we have host identification. Now, every host or device on a network has a name and a unique IP address, often referred to as the host ID. IP addresses are hierarchical and segmented, meaning they contain structured information about the network and the specific host within that network. This makes it easier for routers and subsystems to figure out where to send the data. Step 2, we have routing the packet. Once a device wants to send data, let's say you're loading a website, the sending system consults a routing table to determine where to send the packet. It locates the next hop router, which takes over and begins forwarding the packet toward the destination. Each router examines the network part of the destination IP address to decide which direction the packet should go next. This process may involve multiple routers forming a kind of relay race where the packet is handed off again and again until it reaches the target. Um, Third, we have packet arrival at destination. When the packet reaches its destination system, a few things can happen. If the packet contains the entire message, it's immediately processed by the receiving application. However, in most cases, especially for large data transfers, multiple packets are sent and the receiving system must reassemble them in the correct order. Okay, now um, here we'll continue exploring the like how packet delivery works within a network, specifically how a packet moves from the sender to the receiver, whether it's host to host or router to router. Now, if we talk about MAC address, the local identifier. So every device on a wired or wireless network, whether it's connected via Ethernet or Wi-Fi, which has a unique MAC address, which stands for Media Access Control Address. Think of the MAC address as the physical hardware ID of the device's network interface. When two devices are on the same LAN, they communicate directly using MAC addresses, not IP addresses. Now, next we'll see IP to MAC mapping. So now what happens if a system wants to send data to another device on the same network and it only knows the IP address, not the MAC address? So this is where the address resolution protocol and ARP comes in. ARP is used to map an IP address to a MAC address, allowing proper packet delivery. The sending device sends out an ARP request asking who has this IP, and the device with that IP responds with its MAC address. Okay, now let's talk about broadcasts. So sometimes a message needs to be sent to all devices on a local network. This is done through a broadcast. So a broadcast uses a special network address to signal that all connected hosts should receive and process the packet. Importantly, broadcasts are not forwarded by routers, meaning they only work within a single LAN or subnet. Okay, now that we have looked at how devices find each other using MAC addresses, let's explore how actual data is transmitted on a local network through Ethernet packets, also known as Ethernet frames. Um, this diagram shows the structure of a standard Ethernet packet, the format that defines how data is wrapped and transmitted over Ethernet networks. Okay, now first we have preamble, 7 bytes. So this is the start of the packet. Each byte follows a specific pattern, 10101010, which helps synchronize the clocks of the sending and receiving devices. It basically tells the receiver, get ready, data is coming. Second, we have start of frame delimiter, 1 byte. This signals the official start of the frame's meaningful content. Its bit pattern is 10101011, slightly different from the preamble. Third, we have destination address, 2 or 6 bytes. This is the MAC address of the device the packet is being sent to. It could also be a broadcast address if the packet is meant for all devices on the LAN. Fourth, we have source address, 2 or 6 bytes. This is the MAC address of the sender, the device that created and sent the packet. Fifth, we have length of data section, which is 2 bytes. It indicates the length of the data payload that follows, measured in bytes. It helps the receiving device know how much data to expect. Sixth is data, 0 to 1500 bytes. This is the actual message data, like part of a web page, an email, or a file chunk. Ethernet frames typically have a maximum payload size of 1500 bytes. Then next we have pad, which is 0 to 46 bytes, which is optional because if the data is too short, less than 46 bytes, padding is added to meet the minimum length requirement of 64 bytes for Ethernet frames. Finally, we have frame checksum, 4 bytes. This is used for error detection. It contains a CRC, cyclic redundancy check value, which the receiver uses to detect whether the frame was damaged or in transit or not. Okay, now that we have examined Ethernet and IP, let's move on to one layer up and talk about the transport layer, specifically the two key transport protocols, UDP and TCP. Okay, so first of all, we'll see packet arrival and port numbers. So when a host with a specific IP address receives a packet, it needs to know which application or process should handle it. That's where port numbers come in. TCP and UDP both use port numbers to identify the sending and receiving processes. This allows a single IP address to support multiple simultaneous services or sessions, like a web browser, an email client, and a file transfer, all running at once. Some ports are well known and reserved for specific services, making communication more predictable. Um, Here we have FTP, where we have ports 20 and 21 for file transfers, then SSH, which is port 22 for secure remote access, then SMTP, which is port 25 for sending email, HTTP port 80 for accessing web pages. So when a packet arrives at the host, the transport protocol uses the port number to deliver it to the correct application. So here we can say that like UDP is a simple and fast protocol. It sends packets without confirming delivery. Great for time sensitive tasks like streaming or gaming, where TCP adds reliability, ensuring data is delivered, ordered, and error checked. Perfect for web browsing, emails, or file downloads. Okay, now let's zoom in on UDP, the User Datagram Protocol, which is one of the two major transport protocols in the TCP IP model. Okay, now what is UDP? It is known for being simple, fast, and lightweight, but these benefits come with a trade off. It's also considered unreliable. When we say unreliable, we don't mean that it doesn't work. Rather, UDP doesn't guarantee delivery of packets. So, if packets get lost in the network or arrived out of order, UDP won't fix that. It simply sends the data and moves on. and this makes it very different from the TCP, which goes out of its way to ensure every packet arrives correctly and in sequence. So UDP is also connectionless, which means there's no setup or handshake process before sending data, and there's no tear down after the transmission ends. It's like sending a postcard, you just drop it in the mailbox without calling the recipient first or confirming they got it afterward. This lack of connection setup makes UDP very fast and efficient, which is why it's often used in applications where speed is more important than reliability, such as like live video or audio streaming, online gaming, VoIP, like voice over IP. Okay, now in the context of UDP, packets are often referred to as datagrams. This term emphasizes that each packet is a self contained independent unit of data with no expectation of sequencing or guaranteed arrival. Okay, now let's see that simple visual example of what that looks like in action. So if we break it down, on the left we have the client and on the right the server. Time flows downward on the chart. The client sends an initial request to the server asking for some data, and the server begins responding, like sending packets back to the client with the requested information. So far everything is going smoothly. Now the problem is like a dropped packet. Now at one point marked here with an X, a packet being sent from the server to the client is lost in transit. This could happen for several reasons like network congestion, faulty hardware, a routing issue, or just a random glitch in transmission. Since UDP does not guarantee delivery, the lost package is never resent, and the client never knows it missed part of the data. So why this matters? In a UDP based system, there's no feedback to say, hey, I didn't get that. So you don't know what you lost or what you like, is that the full complete packet or not. So the application must either accept the loss like a video streaming or implement its own mechanisms for detecting and recovering from errors, which adds complexity. Okay, now ex- um, let's now explore the other major transport protocols in the TCP/IP suite, um, like the TCP or Transmission Control Protocol. Unlike UDP, TCP is known for being reliable and connection oriented, making it ideal for applications where accuracy and completeness or data are critical. So TCP isn't just about sending data. It ensures that data is delivered correctly in the right order and without duplication or loss. So, when a host sends a packet, the receiving system must respond with the acknowledgement that we received. So, if that acknowledgement isn't received within a certain time, the sender automatically resends the packet. And this mechanism guarantees delivery even on unreliable networks like the internet. Um, so TCP presents data as a continuous byte stream. This means data is received in a smooth, ordered flow rather than as a bunch of independent packets. The application doesn't need to worry about packet boundaries or network level details. Each TCP packet includes a sequence number This allows the receiver to reassemble packets in the correct order, even if they arrive out of sequence. So it also helps identify missing packets, which the sender can then retransmit. And this is the part of what makes TCP so robust and reliable. Now, um, let's talk about the three-way handshake. Like, TCP connections are established through a process called the three-way handshake. Now, first, the client sends a synchronous packet to initiate a connection. The server responds with a synchronous acknowledgement. The client then sends back the acknowledgement and the connection is ready. So this setup ensures that both parties are ready to synchronize before any real data is exchanged. And just like it begins with control packets, a TCP connection is also gracefully closed using another set of control messages, unlike UDP, which just sends out and forgets. Okay. Um, Now that we understand how TCP ensures reliable delivery, we'll see a step-by-step example of how that process works in real-world data transfer. So first of all, the initial request. At the top of the diagram, the client sends an initial request for data. The server receives it and starts sending the requested information in packets, each one with a sequence number to track order. The first packet has sequence number 904. The client receives it and sends an acknowledgement for 904, confirming successful delivery. The next packet arrives with sequence 126, and again the client replies with acknowledgement for 126. So far, so good. Then a packet is lost. Let's say the server then sends a packet with sequence number 127, but this one gets lost in transit, marked with an X here in this diagram. Now the client doesn't send an acknowledgement, so the server waits and waits. When a set timeout period expires without receiving an acknowledgement, the server resends the packet. This time the packet arrives successfully and the client responds with acknowledgement for 127. Then another lost package. The same thing happens again with sequence 128. So first transmission is lost, no acknowledgement received. Timeout triggers a retransmission. Client eventually receives the packet and sends back acknowledgement for 128. So this is how TCP guarantees a complete delivery. And this example highlights TCP's core strength, like retransmission on loss, use of acknowledgements to confirm receipt, timeouts to detect when something goes wrong, and then sequence numbers to keep everything in order. So one powerful feature of TCP is the cumulative acknowledgement, or cumulative ACK. Like, instead of acknowledging each packet individually, the receiver can acknowledge multiple packets at once. For example, if it receives packets 904 through 908 in sequence, it can simply send an acknowledgement for 908, indicating it received everything up to that point. And this reduces overhead, like minimizes traffic and takes advantage of higher network throughput. Similarly, the sender doesn't have to wait for the acknowledgement after each individual packet. It can send multiple packets in a row, improving efficiency. So next we have flow control, which helps ensure that the sender doesn't overwhelm the receiver. So TCP allows the receiver to tell the sender how much data it can handle at a time. Now, if the receiver's buffer is filling up, the sender will slow down until it gets the go ahead to send more. Next, we have congestion control. Like TCP also features congestion control, which focuses on the entire network, not just the sender and receiver. It monitors signs of congestions like packet delays or losses, and based on this, it adjusts the packet sending rate, either slowing down when the network is busy or speeding up when it's clear. Okay, now as we wrap up our exploration of network communication and protocols, it's time to look at how operating systems themselves can be designed to support networks and even run across them. There are two main categories of network oriented operating systems, and they differ in how they handle multiplicity of machines and how much of that is exposed to the user. First, we have network operating systems, NOS. So, in a network operating system, users are aware that they are interacting with multiple machines. Each system runs its own local operating system, and they're connected via a network. Users explicitly log into remote machines, access shared files, or run applications remotely. So here are some common examples include Windows Server, Unix with NFS like network file system, or early versions of novel netwares. Second, we have distributed operating systems. On the other hand, a distributed operating system hides the fact that multiple machines are involved. To the user, the system behaves like a single unified computer. The OS manages all the distributed resources and processes behind the scenes. Users are not aware of what machine a process is running on, or where a file is stored. For example, Google's internal cluster OS, like Plan 9 from Bell Labs, these are the example of distributed operating systems. But these are more complex. Okay, to close out this presentation, let's revisit the concept of network operating system. Like in a network operating system, users know they are working in a multi-machine environment, and the system doesn't hide it. Instead, it provides tools for directly accessing resources across the network. So accessing remote resources, like we have remote logging, SSH. A user can log into another machine by using a command like SSH, christian.cs.yale.edu, this kind of command. This gives them a terminal session on that remote system. Then FTP, file transfer. They can move files between machines using protocols like FTP, which stands for File Transfer Protocol. Then cloud storage access. Modern NOS environments may also use cloud services where users can upload and access files as needed. So, what is the downside? Like network operating systems typically require users to change paradigms. That means learning to establish a session, use network commands, navigate remote resources manually. So for many users, this can be less intuitive and more complex compared to a seamless distributed OS system. So while network operating systems offer flexibility and resources like sharing, they do place more responsibility on the user to understand and manage the network explicitly. With that, we have reached the end of our session on network organization concepts in operating systems, covering everything from LANs and WANs to TCP/IP, and finally to how operating systems support and manage network environments. So thank you everyone for your attention, and feel free to ask any question or request any clarification if needed. Thank you.